All right. Good morning, everyone. Welcome to our panel on data sharing for spectrum sharing research. This is a joint panel by the NSF Swift PI's meeting program as well as SpectrumX. Um, I'm really excited to welcome fantastic panelists who are working in this area and contributing significantly into both spectrum sharing as well as data sharing in our communities. You may have seen in the program, unfortunately, Nada Golmi from NIST wasn't going to be able to make it today. She sent me an email because of a new time constraint project that she had to attend to, so she sent her apologies. So we have our panelists from both academia and industry to discuss data sharing issues for spectrum sharing research. Part of the motivation for this panel was due to an interesting experience I had while we're working on our research at University of Nebraska-Lincoln. I had to introduce myself first. Sorry, I'm John Moran. I'm professor at School of Computing from University of Nebraska-Lincoln. And part of the reason of this panel organization was an experience I had with a student of mine where we're working on vision information, especially machine learning solutions for vision. So we're using state-of-the-art solutions. If you're working on this area, you may have known the acronym YOLO, which is one of the state-of-the-art AI ML models for image segmentation. And I saw a new paper of all the places on Twitter, which was posted on Archive. And I sent this Twitter post to my student, which was an extension to YOLO, which enables the YOLO to detect objects that it wasn't trained for. It's called YOLO World. 2 days later, my student came back with results from that machine learning model. And by then, probably the paper hasn't even been published. It was on Archive, which got me thinking whether we have similar experiences in our field where machine learning is now extensively used in wireless communication and spectrum sharing research. And part of this relies on open source data model sharing, which this work was able to do. When I was talking to John Chapin, NSF program manager, he mentioned the term frictionless reproducibility, which really fits here. This was a perfect example for frictionless reproducibility for research. So this is part of the reason why we are here to discuss data sharing where we are. Obviously, a data sharing panel wouldn't be appropriate without some data. So I actually asked my PhD student, Sang-Won Shin, who's here, to do some brief analysis of the state-of-the-art of data sharing within Swift projects. This is by no means an extensive analysis. Obviously, we had limited time, but it's pretty good. So the question we were after was, what is the state-of-the-art in data sharing in Swift projects? And what do we mean by data? We're looking at, is the code available or published work? Are the data sets available? And if this is an AI, ML-based work, was the model parameters available? So Sang-Won did an extensive work, went through all the Swift and SwiftSat projects, went through the project's information pages on NSF. These are basically the reported publications, and then went through the papers to identify, first of all, whether machine learning and deep learning was used in these papers within Swift projects, and then whether code was available, data sets were available, and model parameters were available. And out of 83 awarded projects, 329 publications were listed. About a third of them are involve machine learning or deep learning in some fashion, and you can see the way these papers share data. Code, data sets, model parameters. And you also see some papers which are not necessarily in machine learning or deep learning, but still sharing some of the code and data sets they have. We have also found substantial amount of papers that are not necessarily sharing their own data, but their results were based on open source data sets that were shared by others, which also fits into this picture. So to put in perspective, this is kind of the state of the art right now in terms of data sharing. Looks like 9 to 10% of the work provides available data, and another 10 to 11% uses openly available data. But obviously this picture tells us we have a long way to go. There are basically two ways to look at this data. One is we have a long ways to go, maybe to catch up with other disciplines. But also, we learned yesterday from our keynote speaker from Ericsson, even Ericsson doesn't have data because the data providers do not necessarily share available data. So another way to look at it is our discipline is actually, in terms of research, is ways ahead from maybe the state of the art and industry in terms of data sharing. So with this motivation, I'd like to introduce our speakers. Apologies. So I can introduce them properly. We'll have brief remarks by our speakers, and then we'll have a panel for your questions. So our first panelist is Maria Zeleva. She is at University of Albany, SUNY. She's an associate professor in computer science at University of Albany, SUNY. She graduated with her PhD in computer science from University of California, Santa Barbara. She holds an M engineering and B engineering in radio communications from the Technical University of Sofia, Bulgaria. And she leads the UBNet lab, which conducts research at the intersection of wireless communications and information and communication technology for development. She is the recipient of NSF Career Awards, the Dynamic Spectrum Alliance 2019 Award for university research on new opportunities for dynamic spectrum access, and the University of Albany 2019 President's Award for exemplary public engagement. She is the co-lead for the NSF-supported NRDZ partnership, which we have a program for in the Spectrum Week and workshops series, and a founding member of the NSF SpectrumX. Maria?
Stack of laptops and I get to put mine. All right, thanks for the introduction. Good morning, everyone. So I'm gonna make you work. What is data to you? When I say spectrum data, what's the first thing that you visualize? Or that materializes in your head? IQ samples, okay. What else? Spectrograms, right? Power spectrum density, pictures or matrices of some dBs. All right. What else? Modulation schemes, okay? Huh? Time series, yes. I got it all. Okay, so yes, heat maps, power spectrum density matrices, modulations, time series of IQ samples. All of these, you know, we've been thinking of as the sources of data that we have to work with in order to understand issues surrounding spectrum in order to advance coexistence. However, we are not thinking so much about data in terms of the purpose that it serves and in terms of the context in which it was collected. I think these are very important. So, because they really provide important sort of background as to what the data can serve us with and whether it is actually useful for the purposes that we're trying to make it serve. So some example purposes of data I've listed here. So maybe you go to gather data in order to answer how many transmitters are currently actively occupying a spectrum band. Maybe you go to collect data in order to answer what's the modulation of a particular transmitter or set of transmitters. Maybe you're seeking to understand whether transmitters are mobile or stationary. Maybe you're seeking to characterize which transmitter is causing interference onto another one, or how has the aggregate interference in a particular band evolved over a temporal horizon. So all of these are different purposes, and by no means an extensive list of different purposes, but some important purposes that data can serve. And so depending on what's the purpose that data can serve, it needs to be collected differently, right? And so all of these different data formats fit differently to those purposes. I also mentioned the importance of context when collecting data. So understanding how the data is collected inevitably affects how well we're going to be able to achieve the goal or serve the purpose of this data. So some questions that underpin context are around, can I even use this data for model training? Am I going to be able to tell my model what the data entails in order to train it? Or speaking of labels of the data. What was the environment where my data was collected? And then if I capture this environment into a model, am I going to be able to translate what I'm learning from this model into a different environment? So robust to various environments. Does my data truthfully represent what happened in the spectrum? So can I even trust that when I gain some insights from the data, those are actually going to truthfully represent the reality of what happened in the spectrum? Does it have ground truth? When I create an IML model and machine learning algorithm on top, am I going to be able to evaluate even how well it did? And do I truly trust that this data can serve my purpose? And then when I go to other stakeholders and tell them, hey, trust these results, they're actually going to take me up on my word, or maybe go and work with my data's context in order to be convinced. So with that, data has to have a purpose that is, data is meant to answer a question, really. And then data with context helps us determine the fitness of data in order to answer that same question. And inevitably, those kind of work in a closed circle where, once we've created a purpose, we can go and collect data in a particular context. And then once we extract that data from its context, we can still be able to understand what the effects of the context are going to be in answering our question that we posed originally. So with that, we need to both understand and quantify the relationship between data context and data purpose. And we really don't have ways, a whole lot of ways to do that anyways. So I wanted to give just a couple of highlights of why this purpose context loop is important and maybe how we can start understanding it a little bit. This is work, my students keep taking me up on suggestions such as set up 5 sensors and go collect data for, many, many hours and see what happens. So this is a result of that will be presented at InfoComm by Karen here, that effectively looks at, what's your sample retention ratio, meaning how many samples are you going to drop across 5 what we consider low-cost, mid-cost sensor platforms as you increase the sampling rate and you collect data. And so as you can see, for RTL-based platforms, you start dropping samples quite substantially, where even at 2 and let alone at 3 megasamples per second, you've dropped 40% of the data that you meant to be collecting. With USRP, that also tails down well before the USRP maximum supported rate recommendations. And so this effectively would result in us missing spectrum activity that we geared up to go and capture. So not good. This is another example of that work that effectively explores how much ambiguity you introduce in the data that you collect by increasing the sensor's gain. And so on the x-axis, again, for those 5 platforms, we have sensor gain increasing, and on the y-axis, we have ambiguity, and this is a measure that's defined in the papers, and I'm obviously, not going to get into details of that. But the ambiguity of how likely you are to confuse transmitter data or transmitter sample with noise and vice versa grows substantially as you increase, the gain on your sensor. So we need ways to contextualize data collection in order to be able to understand how useful the data is going to be in serving its purpose. And so now you're thinking, well, duh, Maria, metadata, but I thought about that too. So yesterday we talked about the paper that came out of discussions in SpectrumX with a list of very data-excited folks. So these are by no means only our thoughts here. So this is a workshop paper that we presented yesterday that focuses, that broadly tackles, data-driven policy and focuses in part on what metadata we need to start accomplishing this goal. So here are some desired properties for data collection, such as what are sensor capabilities, computational power, mobility, and broadly the environment of a sensor. And what's highlighted in red is what the current metadata standards are able or are looking to capture. So quite a bit of a gap between what we feel as a community we really need in order to be able to contextualize our data and what we're capturing or able to capture right now. And so what we really need to patch up here is collecting more context, configuration, behavior, the environment of the sensor. And pulling in metrics in order to quantify what's the fidelity of spectrum data to serve these purposes. So just to give a little bit more context with one specific spectrum characterization task, and this is some work, old news by now, that basically takes a spectrum trace, like the one on the left-hand side, and seeks to characterize basically every time frequency bin as either occupied or idle, and then reconcile that into an overall transmitter activity detected. So we're going to look into how the performance of this characterization task is affected by this issue of sample drops or sample retention ratio and ambiguity. And in a nutshell, it's affected quite substantially. So what's on the left-hand side, I discussed just a little while ago how the sample rate that you set up on your sensor affects how likely you are to retain samples. And on the right-hand side now, we see the accuracy of that spectrum characterization task as a function of the sample retention ratio. So your ability to truthfully characterize the spectrum really depends on the quality of the data that you've collected, and you need to be able to characterize this quality. Similarly, the accuracy of this characterization task would depend substantially on how much ambiguity you introduce when you set up your sensor gain and other properties, and how this affects how likely you are to get confused between noise and transmitter. And these are just two components of the sensor design that would affect data quality. There's many more, some that we've looked into in that paper, and some that we really hope to continue looking in collaboration with the community. So with that, data has to be with the purpose and a context. So when I give you an IQ file or a pair spectrum density file, that also needs to be wrapped with a context of how the data was collected and how fruitful, what's its fidelity, and a purpose. What has the data, what was it used for? What was the accuracy that was achieved? And now we have data with some words associated with it, or numbers, that we can query back and get to use in our own benchmarks. So how can this help? And that ties with the questions that John posed to the panel. So if we have contextualized data, that can help lower barriers for research entry into machine learning, artificial intelligence and spectrum. Because so far, whoever's been lucky to do this kind of research was expected to be able to also get the data. And this is a really, really steep learning curve to overcome, as maybe any of the students here would contest to. Open data with context and purpose can also make data more easily searchable and applicable. So when I want to run a competition of, and engage a bunch of spectrum researchers that dabble specifically in AI, ML, but don't know how quite to collect their data, I can search a database and grab all the relevant, data that would help me with my competition. And so, in order to advance this, we need to sit down and find those purposes and those contexts that are important. And so, a shameless plug, speaking of sitting down, there's a research community for it that SpectrumX is organizing. So I highly advise anyone who's interested in AI, ML, for Spectrum to engage with this research community. And one more shameless plug, the National Radio Dynamic Zones conversation has been ongoing for now 4 years, and we have an event planned at the Green Bank Observatory where we'll continue pondering upon issues of spectrum coexistence, and data and characterization obviously are going to be key components to that. So if you see me or the Chris's, who I think are here, talk to us more about how to engage with this event. There is the agenda on the QR code there. I have cool swag for anyone who, submits an abstract before NERSCOM. I mean, no, but I do have swag. So please engage. So with that, thank you.
Thank you, Maria. Our next panelist is Kaushik Chaudhary from Northeastern. He's a professor in the Electrical and Computer Engineering Department at Northeastern, faculty fellow in the College of Engineering. He was a finalist for the 2023 U.S. Blavatnik National Awards for Young Scientists. He was also winner of the U.S. Presidential Early Career Award for Scientists and Engineers in 2017, the DARPA Young Faculty Award in 2017, the ONR Director of Research Early Career Award in 2016, and the NSF Career Award in 2015. He has received several Best Paper Awards from several IEEE and ACM conferences. He's a member of the NSF AI Institute for Future Edge Networks and Distributed Intelligence, and is lead PI for the NSF RF Data Factory Community infrastructure project that aims to release data sets and software APIs for RF data collection and community. He's a fellow of the IEEE. Kaushik.
Okay. Well, thank you for having me here. Thank you, John. And it's always a tough act to follow Maria, so no thank you, John. So I'm going to talk about some challenges, and I'm going to offer my take on them, if not the solution, at least my take on them, and really challenge the community to think about whether this makes sense or whether we should follow a completely different radical approach. Okay. So first thing is, and I'll start out by saying, let's get to the crux of the problem. Right. When Maria asked, what do you think of when you think about RF data, right, or spectrum data, and you think about IQ, and when you start to think about IQ, you cannot forget the ECPA, which prohibits intentional or actual interception of wire, oral, or electronic communication. And you can interpret this in different ways. And this interpretation is what creates some difficulties for us to save IQ samples, distribute IQ samples, and so on. The very act of storing an IQ sample may or may not violate this. It's an open policy and legal debate. But okay, well, what is it that we can do as engineers and scientists to circumvent this problem? So one solution is let's take out any discriminative information that could be used to trace back to the original sample level, what exactly was transmitted. So, we discussed some methods earlier. So one clear method is to use spectrograms, right? So you throw out, say, phase information, and you capture some essential characteristics of this, of the signal, and try to make some inferences on it. So that's certainly one way, and towards the end, I'll suggest a different approach, and then we'll see whether you buy that or not. Okay. Now, where do you find all these data sets? Okay, so again, since we're in the business of shameless plugins, let me do so as well. This is an NSF-funded infrastructure award. We call this as RF Data Factory, and I'll walk you through some examples towards the end if you have time. But what you find here is a resource for the community that you can submit to us your RF data sets, tutorials that you have recorded in which you show how to use your data sets. There is a rich library of software APIs where you can enable the community to collect their own data sets or clean up data sets. And so all these exist today, and I'll show you. It's very easy, navigable system. You click on your choices, and it shows you options that are relevant to your choices. And then finally, there are various workshops that we hold. We take in community inputs, and your inputs are really valuable as we make this as a resource that all of us can use. All right, now here is my confession, John. All the papers that we have produced as part of Swift have their data sets released. That's the proof. However, you make a good point. Without trained model parameters, it's very difficult to compare on a 1:1 basis, and that is something we as a community should be doing more. So that's a point well taken. All right, now let me come to the challenges, and I promised you that I'll offer some challenges and some solutions. So the first one is where do you collect data, right? And so I want to point you, there are a number of very exciting resources that any of us can use to go and engage in data collection efforts. And so here is an example of the NSF Power platform, which is, and this particular example is from Powder, which is in Salt Lake City, Utah. But it's not just enough to say, go and collect that data. So on the links, you also find an example data set that was collected on Powder. And then you see a tutorial on how did you collect that data set on Powder. So that next time, if you are an interested party, you can just follow that tutorial and see the data and collect it yourself. So it's important for us to enable the community to do more of these activities. And so the one below, at the bottom, you see the Colosseum, in which again, there is a tutorial on how do you set up these different Docker containers that run your stacks, and you can collect this data for your own on your own purpose. So lots of good resources exist, and we want to make sure that we as a community develop more of these tutorials and democratize access to data. Now, here is another way in which you can collect data. So not all data needs to be collected in large-scale platforms, right? You don't need 100 nodes. Sometimes you just need to transmit something in your own lab in a much smaller setting. But as again Maria referred to, there are a number of different settings and parameters. And if you have played with software-defined radios, you know that if you don't do calibration right, if you don't set up the correct buffer length or the sample size, you're going to drop packets, and it's going to lead to all kinds of problems. So here is an API that you can just go and press a few buttons, click, 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 and it sets up your own test bed, and it synchronizes all the nodes, it calibrates, it generates the data, it also generates automatic metadata files, which is stored in each of these sample transmissions. So it takes care of the plumbing that not all of us need to do. Again, the source code and the data set are all released as part of your, as a service to the community. And I think we need more tools like this. All right, second one is to build consensus on metadata. So your data is only, or your reusability of data is only good as the quality of the metadata. And it's an open question as to how much information are you going to put in that metadata field. So we try to follow the NTIA SIG-MF standard when it comes to core RF signals. But this is clearly an evolving field. New kinds of antennas and hardware and environmental conditions are coming in, and how much to capture. And it is not just the RF world, and I'm sure you're going to hear more from my colleague Ahmed later on, but when we talk about data, we have to go even beyond RF data. Now it's a question of cameras and LiDAR, which are capturing the same scene in different levels of fidelity, in different modalities. And can you fuse all this together to create one rich representative data set? And then what would the metadata here look like? So there is a challenge to build consensus, especially if data transcends RF and goes into other modalities. And there is no reason why we should not be doing it. The third challenge here is, and this comes back to this original problem of sharing IQ data. Now, here's my experience. I was a performer in the DARPA Rift Mills program and later in the IARPA program, where we had access to up to about 4 terabytes of rich data collected from over 10,000 devices in the wild, lots of interesting channel variations, signal strengths, and you could use it for a number of different purposes. But this incredible opportunity could not be shared outside. So a lot of our papers, we could not release this data set and say, look, here is this cool new works on fingerprinting. You can replicate our results, or you can do better on our results, but use this data set. We couldn't do that, right? So what could we do to share this? And so here is my challenge proposition. What if we don't share raw IQ data, but we extract characteristic features and we create a library of these representative features through a feature extractor, and we share those features for further model training? And you can use, if your feature set is representative enough, you can use it for a number of different tasks. And there are a lot of questions here, right? Can you go back and recover the IQ? So there are exciting challenges that we would need to answer as a community, but this might solve the problem of storing and releasing raw IQ data sets. And so you could imagine that an operator would be open to, or I can't say for them, but they might be incentivized to release a whole library of features at different levels of resolution and fidelity, and allowing other performers to finally use them. And my last challenge here is, fine, you got all your data, you trained all your models, but how do you trust whether what you did is actually latching on to the right parts of the data, is actually doing what the model is trained to do? It's not learning the channel if you're doing RF fingerprinting, right? How are you going to verify that? So we need tools that do some sort of forensic analysis. Given this data and the model, I should be able to point to that point, to one sample, and then look what is the model actually doing. And you can take in time series IQ samples and put a spotlight on where the model was reacting. And so here is this example where you're trying to detect these cute little puppies, right? And you want to understand where in the picture is the model picking up that response. And so this is what we call as class activation maps. And you can see the heat maps where the model is responding to when you give it the class of a puppy or the label of a puppy. Now, could we do that same thing for RF data? And this is a tremendous opportunity and would be a valuable tool for the community, so that you find data, we find ways to share data, and we find ways to test our models on the data. So with that, I'll stop here and hand it over. Thank you.
Thank you, Kaushik. Our next panelist is David Debrecht. He is the Vice President of Wireless Technologies at Cable Labs. He has over 35 years of experience with wireless technology solutions in both government and commercial applications. He has served in a broad range of technology and product development roles, including various positions in R&D, product management, and technology development. David started his career at General Dynamics, developing radar warning, and electronic countermeasures platforms on the F-16 fighter aircraft. He moved to the communications industry in the mid-90s with Nokia, developing radio base station solutions, and he successfully filled many different roles within Nokia for 25 years, latest of which, before moving to Cable Labs, was being the CTO of the US and Federal Business Organization. David?
Thanks much, appreciate it. So I appreciate the opportunity to come talk today about spectrum research and data sharing. As was just said, David Debrecht's my name. I come from a little bit different background. I'm not an academic, came from industry, been in industry for a long time, but I have been in government industry, wireless industry, and now wired broadband industry, which in my opinion, the wired broadband industry is actually a wireless industry as well. As we talked about earlier today, 80% of your data that's coming to you on your phone, your laptop, whatever, are coming over wired networks. It just happens to be Wi-Fi. That's that last 100 feet, last 1,000 feet of connection. So definitely wireless industry, no matter where the data started. So Cable Labs is a nonprofit research and innovation lab for the broadband industry, and it's heavily invested in spectrum and spectrum use innovation, spectrum research. The ultimate goal is to develop new technologies and approaches that enable more intense usage of and greater access to scarce spectrum resources, transforming spectrum from a bottleneck to an enabler for innovation in the broader community. To achieve this, we need to encourage new R&D instead of repetitive R&D. A shared repository of or a database of research findings and measurements and underlying data is really key to achieving that. This would not only avoid duplicative research, but it would enable a diverse set of stakeholders that can identify new problems and focus areas in a timely manner so we can take on new challenges as opposed to continually repeating and redesigning existing systems. Public access to data regarding spectrum usage, including across time, across frequency, across geographic location, power levels, et cetera, by federal and non-federal users is foundational to spectrum sharing and innovation. Such access will be a game changer in multiple areas for spectrum research. A building block for creating new spectrum access and management systems, interference mitigation techniques, and will enable access to spectrum by new users more quickly. Spectrum situational awareness at scale does not exist today, creating a significant gap between those who have access to certain data and those who do not. Spectrum situational awareness is often unavailable to both private sector and the federal government. Both sides of the equation, as we talked about earlier today, are lacking information. There's no one data source that can provide accurate information regarding time, location, frequency of spectrum use by existing users, nor are there technical parameters available for deployments or underlying service. We just don't know where everything is. We've all seen the FCC map, and that's about the best granularity that we know. Somebody's using this spectrum for something. We really don't know why or what the parameters are. This information is key to creating a baseline for focused modeling of shared frameworks and efficiency and improvements of spectrum use. This usage information really is just a starting point to really better understand how to increase intensity of the usage through spectrum sharing approaches that we're talking about today, and will require a deeper understanding of the incumbent systems. As an example, to understand if a shared approach is possible, we need to have the technical data on incumbent systems' resilience to potential interference, which likely includes data on receiver characteristics and performance of those incumbent systems, which we do not have today. Relying on historical rules of thumb on thresholds for receivers leaves too much spectrum on the table, given the growing demand for spectrum resources and their importance in the broader economy. The National Spectrum Strategy Implementation Plan focuses on collecting information from federal spectrum users, but licensed private sector users should also be required to update the spectrum usage and deployment data, whether through the FCC's universal licensing system or a new database that can host and provide information to all about a particular band's usage. The ULS interface today is outdated. ULS hosts a trove of useful information, but is cumbersome, and the interface renders much of the data very difficult to use. It can be improved with modern user-friendly dashboards and search tools to improve transparency and analysis of the existing data that we have today. The development of robust APIs to interface with ULS and other spectrum-related databases that are out there today would also encourage third parties to build applications that analyze and present spectrum-related data in new, innovative, and novel ways to further improve transparency and insight into our spectrum usage and how we can improve on it. Data quality is also key in spectrum R&D projects and requires more frequent updates of the data that's in ULS and other databases by licensees so that the information in the database is both accurate and adequate. In addition, historical data should be made readily available. Today, it is difficult to analyze historical trends from currently available ULS data. Testbeds, research infrastructure, and collaboration support can provide a similar incentive to parties to reach significant state-of-the-art successes in the area of spectrum research, which we're lacking today. Neutral testbeds that provide a platform and resources without bias towards a particular use case give the community an opportunity that individual parties may not have today. This is also directly leads to support for collaboration and ongoing coordination of our spectrum use. Spectrum R&D projects should not cease at the end of a contract or grant. Instead, those lessons learned should be brought back into the system. The protocols, the technologies, and the data that we have should be then shared with the larger ecosystem to advance. And instead, like I said earlier, instead of being repetitive R&D, we actually advance with incremental R&D to new, efficient, and diverse uses of spectrum. Artificial intelligence and machine learning can be powerful tools to mine unstructured data and digest it into a more user-friendly format. However, AI models are only as good as the underlying data, and today that data is not very good. So accurate and up-to-date data is critical. Of course, we want to be more comprehensive and have more accurate data, but at the same time, we have to continue to drive new technologies and new approaches to that spectrum access. In the pursuit of increased data and data sharing, we must always take a risk-informed mindset as we contemplate new spectrum access regimes. Thanks much, and I'm looking forward to the panel discussion later.
Thank you, David. And last but not least, our next panelist is Ahmed Al-Khatib from Arizona State University. He received his BS and MS degrees in electrical engineering from Cairo University, Egypt in 2008 and 2012, and his PhD degree in electrical engineering from University of Texas at Austin. In 2016, he has worked in the connectivity lab at Facebook before joining Arizona State University, where he is currently an assistant professor in the School of Electrical, Computer, and Energy Engineering. His research interests are in the broad areas of wireless communications, signal processing, machine learning, and applied math. He is the recipient of the 2012 MCD Fellowship from the University of Texas at Austin, the 2016 IEEE Signal Processing Society Young Author Best Paper Award for his work on hybrid precoding and channel estimation in millimeter wave, and the NSF Career Award in 2021. Ahmed?
All right, perfect. So thanks everyone for joining, and thank you very much, Jen, for the introduction. So today I would like to briefly highlight some of the, I think, important considerations for data sharing in communication systems, and also some of the data sets that my group has been building to address some of these considerations. So first consideration, let's go to it directly. So wireless data sets need to capture various configurations. And this is, I think, a very important difference compared to other machine learning areas in computer vision, NLP, and speech recognition, where it's very clear what we mean by image or text or audio. So in wireless machine learning, so what we mean exactly by wireless measurements is not very clear, as also Marianne kind of touched on. So do we mean basically raw data, channel, IQ, or do we mean physical layer features like RSRP, power measurements, or SNR, or do we mean higher layer features like throughput or latency? So it's different machine learning tasks basically, of course, will be interested in different types of data. But since a lot of the innovation in machine learning is actually also happening in the pre-processing and normalization and different feature extraction aspects of the data. So in my opinion, it's important to provide this data as raw as possible. So the rawest as possible is the better, because we can always, or in many cases at least, derive the high-level features from the raw data, and also allows the innovation in how these data is, how these features are extracted. Another important, now of course this is also challenging, right? Because the rawer the data is, also the harder it is to acquire for different reasons. Another important aspect of wireless research is that typically we are interested in developing and analyzing these solutions in different configurations. So for example, I would develop this channel prediction model, and we would be interested in maybe evaluating its performance in different number of under different number of antennas, or maybe see how it extends to other systems and other frequency bands. So in that sense, it is, in my opinion, our problem is harder than computer vision. So we don't just need one ImageNet. We essentially need a collection of ImageNets, right? And to cover the different use cases and scenarios and enable innovation in different areas. So another important consideration is that in many cases, these wireless data sets need to be site-specific. And the reason is that in many applications, whether we're talking about beam prediction, channel prediction, or resource allocation, and proactive handoff, in many of these applications we see that machine learning shines mainly when these models are trained on site-specific datasets. So datasets that basically capture the specifics of the site, the geometry around the base station, the mobility patterns of the users and scatters, and so on. So that's kind of compared to just training these models on 3GPP-like statistical models. So, so this is an example, for example, for CSI compression gain. If we train these models just based on just one data set from all sites, or if we particularly train these models on the zones that or the areas, the regions that these CSI compression feedback models will operate on. So the model architecture itself could be universal or adaptive, but the training of the model in many cases benefits from site-specific datasets. Okay, so in order to somehow address these two considerations, we built DeepMIMO around 5-6 years ago. And DeepMIMO is not a dataset, it is a dataset generation framework. So it's basically, it's a framework for generating data for different scenarios. And it accepts as what we call a DeepMIMO scenario. And the scenario is basically a high-fidelity synthetic data set generated for a particular area or region. And so far we have around 40 scenarios in DeepMIMO covering different use cases, and including dynamics and polarization and Doppler. And given this scenario, the researcher basically sets the parameters, including antenna configurations, what base stations to activate, how many antennas, orientation, polarization. We have also a DeepMIMO version that supports 5G and R frame structure, and so on. And then based on these parameters, then in typically a few minutes, this generator generates a data set, DeepMIMO data set, that includes the channels between all base stations and users, line of sight, non-line of sight status, and a lot of other data types. So the good thing here is that this is site-specific data set, because it's based on particular sites and regions. And it somehow allows for this different and various configurations, because we have different scenarios from different locations and also different configurations and parameters. And it does all that while being also very simple to define and reproduce. And this kind of frictionless reproducibility, right? That if we, once we, basically a researcher says, okay, I use scenario X, and these are the parameters, then any other researchers that use the same scenario and set the same parameters will reproduce exactly the same data set. And then it will make it easy to kind of compare and benchmark. And so this week, actually, we just released the third version of DeepMIMO that supports polarization and Doppler, in addition to 25 more scenarios. And I think so far we have around 40 research papers that actually used DeepMIMO, and including from 200 different research groups that actually we counted them. All right, so third consideration is that in also looking at future kind of applications, it's important to integrate communication data with other sensing modalities like radar, and not just radar, but also LiDAR, vision, position, IMU data, and different types of data. And this allows to explore basically different applications, all the way from the coexistence of these different modalities, especially the ones sharing the same spectrum, communication, radar, and also exploring how these different modalities can help, for example, communication systems, how the visual data or the LiDAR data or the radar data can improve and provide some perception for the communication networks. So in order to do that, we need to have a data set with coexisting data from communication and all the other sensing modalities, synchronized and calibrated. So with that motivation, we built also DeepSense 6G, and I think released more than a year ago now. And DeepSense 6G is essentially a collection of scenarios. And it's different than DeepMIMO. DeepSense is based on real-world data. So it's a large-scale, real-world, multimodal sensing and communication data set. It now has more than 1.5 million multimodal data points. And so each data point basically does what I just mentioned, that has communication data and also the other sensing modalities from, so for example, at the same time that we have this wireless communication channel, we have this data, this IQ radar information, and they have this LiDAR scan and image and so on. And so DeepSense is a collection of scenarios. So now we have around 44 basically data sets. We call them scenarios. And each scenario is a large data set collection session collected by different testbeds. However, an important point is that all these testbeds follow the same kind of standardized way in data collection. So we try to standardize the way these testbeds are collecting the data. And so that the data produced by all these testbeds go through exactly the same post-processing pipeline and then generate exactly the same data structure. And this makes it easy for basically incorporating more data from other research groups, as well as it makes it very easy, for example, to merge data from the two different scenarios or study transfer learning and many kind of interesting applications. And these 44 scenarios actually not collected just by our group. We have now collaboration with a few other groups, and we look forward to collaborating with more in sharing our testbeds and how to construct basically replicating the testbeds and sharing and integrating the data sets. Right, let's skip this maybe. So this is an example testbed we have in DeepSense. So we have four, this is for V2V data collections. We have 4 sites in this testbed with millimeter wave phase arrays, radar, 3D LiDAR, and 360 camera and GPS RTK. And then again, so the data collected from all these sensing modalities are synchronized so that we can generate such data set with synchronized data from LiDAR, vision, millimeter wave phase array beamforming, radar, and position information. Fourth and last consideration here is that, in my opinion, no matter how many data or how much data we can collect in real world, they will never be sufficient to cover every use case and every scenario and every corner case. So that probably motivates the need for digital twins that basically digital replicas of the same site and the same deployment, where we can use this digital replica or digital twin to explore a lot of interesting applications on data augmentation and kind of exploring the different cases that are hard to get real data for. So for that, we have been also building this new data set called DeepVerse 6G. And DeepVerse is similar to DeepSense in the sense that all the data modalities from all sensing and communication are synchronized. But a key point here is that we built some of the scenarios in DeepVerse. So it's a synthetic data set. But we built some of the scenarios in DeepVerse to be digital twins to deep sense scenarios. So this is an example scenario where we have a deep sense scenario on the left. So this is real world data. And then on the right, we have deep verse. So that's a digital twin. And this is not just about modeling the visual scene. We also try to model the hardware and antenna characteristics. For example, we take the phased arrays that we use in measuring and collecting the real world data to the anechoic chamber. We measure the beam patterns and incorporate this model in the digital twin so that we can get hopefully realistic kind of digital twin or calibrated digital twin. And this is an example data that we generated from this digital twin. So this is the real data beam power measurements across different beams. And this is the synthetic or digital twin data. Now, the good thing in the digital twin is that we don't have noise. So we can now measure and basically analyze and study, for example, the performance of whatever we develop across, for example, different SNRs and so on. All right, so with that I conclude. Thank you, and I look forward to the panelists.
Thank you, Ahmed. We'll invite all the panelists to the platform. So thank you all for your insightful comments. So I want to kick off with maybe stealing from Maria's first question. What is data, but maybe slightly changing. What should data look like for wireless research? Maria, you mentioned about collecting data with purpose. Kaushik, you had a really good caution about what we can and cannot share and whether we should share the data or maybe the data models. David, you mentioned data quality. That's really important. And Ahmed, you mentioned site-specific data sets even. So wanted to get your perspective on what you think data should look like. So borrowing from other communities, we have, for example, in image processing, MNIST and CIFAR and ImageNet. And you had a great comment about whether we should have those standardized data sets or whether we need to look at it from a different perspective. So what do you think should data look like for our communities?
Go. Yeah.
On the spot. All right. So what our community's data currently looks like is a paper with a data set, and the data set is, you know, just power spectrum density or an IQ samples. I think what it should look like is, you know, that data set dressed with how it was collected, you know, if it was on a real sensor platform, what exactly the sensors were, how they were configured, and what was achieved with that data on top of that, in terms of, you know, what model was developed with its parameters, what accuracy indicators were achieved, you know, and once we have these sort of data dressed, as I said, in its purpose and its context, you can use it as a package. So instead of, you know, having John's student go through, you know, the extensive and remarkable work that he did, you know, maybe you can launch a query on the wrapper and quickly know, you know, how much data you actually have in order to work with for whatever new purpose you're trying to achieve.
So what should data look like? Let's answer it in two ways, right? If this data is provided by someone who is reluctant to share data, then it looks something different. And my take is that it need not be IQ. There could be different ways to capture the inherent rich representation of IQ in other ways, which is more purpose-oriented. Okay, so it's not this doesn't mean that you strip away all the good parts of it. We still retain it, but just enough for what we want to do. And as I mentioned, there could be different ways in which we can extract characteristic features, not hand-engineered, but let the machine figure out what are the key characteristic features, and then you do what you want to do. But now on the other side, if this is data that you have collected and you can collect yourself, then also provide, with this data, also show how did you collect it by releasing code or other ways in which that a similar kind of collection effort could be done. There is no greater teaching moment than allowing the person who's student often in our cases, to go and replicate that collection effort and experience these different knob turnings that had to be done for that data to be collected. So data collection by itself, yes, we'll have metadata, but also supplement it with collection code or collection experiences which are integral to replication and further work.
Yeah, so from my perspective, I think the answer would be it depends. And it depends on what you're trying to do with the data and what the purpose is and what you're trying to get out of it and where you're going. When you go back to the concept or idea of spectrum sharing and how do we make spectrum more available to more users and actually share the spectrum that we have today, the data probably should look a little bit more like what are the parameters, what are the characteristics of your transmitters and your receivers out there in the different bands, and what are the purposes and use cases of the different bands, so then you can go off and do the analysis to determine what can be shared, how can it be shared, and what are the best mechanisms for doing that sharing. Is it real time, is it non-real time, is it geographical based, is it time based, et cetera, so that you can actually make better use of the spectrum we have available.
Yes, so I don't repeat basically, I can just agree with what Mary and Karsh especially mentioned about the context, right? So in my opinion, as long as we can provide raw data, so the rawer the better in that sense, because we can always derive the other features and innovate also on how these features are extracted and how the data is processed, which is kind of, in many cases, actually found that this is a core part of the innovation and the contribution is in how we process the raw data to extract important features. So as long as the raw data is available, so it's important to share, I think, this part of this type of data. The other aspect is the context, as Maria mentioned, and to make sure we also collect data to enable certain tasks. It might be hard to just have data for every task, right? I mean, most probably we collect data with certain, at least set of tasks in mind. Yeah.
Thank you.
Can I chime in with something?
Absolutely.
I just wanted to amplify something that's come up in discussions at SpectrumX and is in part within that policy paper that I mentioned earlier. So, I mean, we have data, right? So that's kind of the core of it all. And then we have these spokes coming out of the data now, like the context, what can it be used for, what piece of code was it generated with, what piece of code was applied on it, right? So something that came up in this data-driven policy discussion was this notion of DOIs, right? Data object identifiers. All of our papers have it. That's how ACM and the publishing agencies basically track papers down to authors. So Dirk Grunwald actually coined this. It was like, well, can we come up with DOI for data so that and I think his idea was so that we can attribute those IQ samples to whatever products came out of the IQ samples. But there's more to it, or there can be more to it in using this concept, right? You can now track a piece of data to the model that was employed on it, the performance characteristics, the code that was used to generate it, all of that. So as we create all these modalities, maybe metadata is not going to be enough, and we'll have to have different components that ultimately should be easily trackable to one another.
Thank you. Let's see if our audience have questions.
Julie Jan from University of Minnesota. So again, I completely agree with Maria, that we had to kind of share data with a purpose, right? So, but I want to kind of brought back the purpose in a much more broader sense, right? So there's oftentimes, I think, a lot of discussion here. We share data for the purpose of academia writing other papers, right? But I think also there's also the data we have to share for example, help industry to improve a lot of deployment or actually develop the next generation technology. So, I mean, we do a lot of commercial management with collaboration, Monisha and other, and we actually got our approach from the industry. They realize a lot of things we are doing, they don't actually have that data. And privately, they're willing to share some data with us not share with us, actually collaborate with us to kind of do some research. I mean, the purpose, I think partially because the problem with the NSF funding mechanism, right? So if you try to measure the existing system, it's not sexy enough. And oftentimes if you write proposal to try to say, hey, we want to understand what's going on in the real world, how spectrum actually being used, what's availability of different spectrum, et cetera. The proposal oftentimes not getting rated very high. It's always the next shining kind of object. I want to develop a new type of kind of devices, whatever stuff would be much more interesting from the academia point. So the question of what I'm trying to kind of ask you guys to think, what are the things we look at, especially maybe from the industry point of view, how can we actually getting more real world data, getting the community kind of collect, share data. We mostly ask a lot of poor undergraduate students have the kind of to do a lot of measurement, drive around, collect a lot of data, but using some funding, we're getting some industrial gift fund to do some of the measurement, but it's generally much harder to kind of do large scale measurement, right, without a lot of funding.
Thank you.
Yeah, I guess I can jump in on that one. It's a great point, and it is very difficult to actually go out and do measurement large scale. We're actually working on a project right now to develop a very small and cheap way to measure and then you put that device, let's say in various locations around a city where spectrum is actually being used to see what it is. And so far the results are showing us that yes, some of the bands that we think are currently being used are being used, and yet some bands that we think are being used are pretty much empty or quiet. And we need to actually see what spectrum is being used. And like I said earlier, it's kind of a two-stage approach. You look at, on the front end, what we think is going to work. You do the simulations and the receiver transmitter characteristics. And then on the back end, actually go out and measure in the field where you know those transmitters are actually supposed to be. And can we do different things in different environments, indoor environments, outdoor environments, urban environments. They're all very different. So getting those measurement tools out there, I think, is going to be key for utilizing as much spectrum as possible.
So let me chime in and maybe augment this discussion just a little bit more. Imagine you want to do spectrum sensing across a wide area, okay? And the operator wants to use the results for something else. You know, who knows what it wants to use it for. Now, how do you engage citizens to be part of this collection effort without actually deploying an end-to-end hardware, let's say? Now, as I said, right, so yeah, I mean, you can collect IQ samples, but then who knows who might sue you for that, right? So how about, again, going back to this feature extractor idea, let's say we have a larger model, we split it into two, you have a feature extractor and you have a model head, okay? Let the operator train this entire model and give out the feature extractor to anybody and everybody in the community. And so what the community person does is simply captures these features and then sends it back to the operator. What the operator does at the end is hidden from what the community sensor is doing or a citizen scientist is doing. So you can be engaged, but yet you do not need to have the full picture. That's one way to look at it. If you want to do, if company wants to, if an operator wants to invest in data collection efforts without fully revealing all their cards on the table. But there are other modalities as well. So.
I mean, in my opinion, this is, you know, it's great, of course, if we can get real data from operators, but in many cases, the innovation, you know, is on new areas that maybe even the current networks that are deployed are not supporting. So I think there will always be this kind of need to have our own test beds, large-scale test beds, set-scale test beds, where maybe operators can also help by providing some, you know, some of the equipment they have, but we can augment this with other systems that, you know, that really captures this new aspects that we are interested to collect data for, and then we'll have full control over, you know, tuning the parameters and activating, deactivating, and testing, having really data sets that stretch, capturing different cases. So I think that there will always be this need to build our own be somehow standalone and independent.
Yeah, so many challenges there. Maybe one final question from the audience? Ali?
Thank you. I would like to point out at least one discussion here in terms of the requirement for the IQ data, going for that, or the feature extractor, especially Kaushik is mentioning. But for 50 years in signal processing, we are already doing feature extraction. Features, engineered features are given to us, and we are developing pattern recognition models for those, right? The real promise for the deep learning approaches is the model itself learning those best features out of the raw data. So, I mean, and the learned features, whatever the, let's say, industrial partner or data generator, if they give us the features, then the only model left for, let's say, computer scientists or signal processing is to develop different models on those features data, not really going for it, for deeper understanding. And most of the features that you need to take are dependent on the task that you need to ask at the end also. And looking into all of these things, I think we really need the raw data, the IQ data, and the promise seems to be really the systems learn from which features are best directly from the IQ. So do you think really IQ is the best in terms of data sharing, or should we really go? I understand in some cases problems saving the IQ, for example, for radar data or other things, it might be challenging to take it or save it or share it, but at least for civilian applications. So what is your take really? Because this is an important point in terms of data sharing for IQ or the features only.
I jump in? Okay. I can't agree more. I think part of the innovation, and I think Ahmed talked about this as well, is there's two components to it, and one is feature design. And without having access to the data, we're quite limited in what features we can design. And feature design can be quite powerful. I mean, if you think about how we collect data, currently the way we extract features from spectrum data it imposes stringent requirements on how the data should be collected. For example, we've been doing modulation recognition with cumulants, but cumulants break the moment you don't observe the transmitter in full, right? So what new feature can you design if you only had half of the transmitter's bandwidth observed? That would be a question you can tackle on top of IQ, not on top of other features. So yes, I agree. The more we can get access to raw data, the better. But that doesn't need to be the only way we do it either, right? Innovation can happen on top of features as well, and I think it's just our job to find the sweet spot of the mix, so that we can move forward.
Thank you. I know we are standing between you and lunch, but I want to give one final opportunity for the panelists for their final remarks, especially considering that there are several students in the audience. So what are your message for the next generation in terms of data sharing? Maria, we can start with you. Oh, sorry.
What is my message in terms of data sharing? It takes time, but it has a huge impact. Sharing data itself is not going to grant you publications right now, which is kind of unfortunate, unless there's a special issue here and there in a magazine. But if you are looking to create impact from your work, spare the week to clean up your data and put it on, and that's going to get the citations and the visibility of the data that your work truly deserves.
So I'll just say this: trust in the models that you're building is a big deal, and if as a community we need to show that there is a pathway where AI/ML is being successful at some critical tasks which decide safety and economic prosperity of the nation. you have to show trust. And to show that, the best way to do this is to create reproducible results. And the next step for that is to, collect great data, make sure that data is well calibrated, good metadata exists, and it is shared, and even code that you use to develop your models on it is also shared. And with only that will come trust and verifiability. So important things that I think we should all embody in our future papers as well.
Yeah, from the industry perspective, I guess what I would impart to new students is spend more time determining what problem you're trying to solve before you just go off and collect a bunch of data. Because if you don't know what problem you're trying to solve, then the data isn't worth the time and effort you put into collecting it. You won't get the results out of it that you were expecting you can get.
Yeah, I mean, I think a few points. So agreeing with other colleagues mentioned, the quality of the data, I think, is extremely important. And this could, like the results could be actually completely misleading if the data that we started with in developing and analyzing our machine learning or signal processing algorithms are not really credible. So I think the credibility of the data is very, very important. So that's for, in terms of choosing what data set and what data to start with. And then for data actually generation, construction, and collection, the good thing now is that there are already initiatives for data collection and trying to kind of standardize and share also, like, not just data sets, but also the test beds that are used to collect different types of data. So instead of starting from scratch, I think leveraging some of these initiatives could somehow save some time.
Thank you. With this note, this session concludes our NSF Swift PI's meeting. I'd like to first of all thank NSF for their support, especially Hussein, John, and I don't know if Huayu is here, for their great support. And I'd like to invite you to the podium for final remarks. John is coming here. In the meantime, let's thank our panelists.
So I'll just say on the topic of, maybe I'll speak to the topic of this session, and you could say thank you for all of Swift's
I'll just
meeting.
say thank
Yeah, great. So NSF, we at NSF have been sort of growing our attention on this data area. Thank you very much to John and all the speakers for a very interesting set of talks here. I wanted to point out that we've dipped our toe a little bit into being a little more intentional in this area with something that we put into the new Spectrum solicitation this spring. I'll just read a little bit. Sharing of data sets that are appropriately labeled and documented, and sharing of code using mechanisms that enable frictionless reproduction of results are important accelerators of research community progress. Proposers are strongly encouraged to consider how their projects can contribute useful data sets and enable frictionless reproducibility. Other key accelerators of research community progress, ... Proposers are invited to submit proposals in which progress towards such accelerators is a significant outcome or even the primary deliverable. So we're starting a little bit in the context of New Spectrum by saying we care about this. You as a community help us move in this direction. But we could be much more intentional in the future. I mean, we had the comment from the professor from University of Minnesota that he's like, well, we put proposals in for this and the panels never fund them. Well, the way to fix that would be to have a dedicated call focused on that. And the way to get there would be to have a workshop. So challenge to the community. If you think that it's worth organizing a workshop specifically on data for Spectrum, which would produce a workshop report that would then stimulate NSF to do something dedicated in this area, well, work with us, come together with a proposal, and maybe we can make something happen in the next year or two. So with that, on this topic, I'll let Hussein close the whole SWIFT meeting. Please.
Thanks, John, and thanks everyone, especially John, for organizing this exciting program, and for everyone for contributing. Also about data sets, I think I just want to say one more thing. There is a perspective of seeing data sets as an infrastructure. As a resource. Of course, we're not the only community that needs data sets. There are other communities who consistently and for a very long time relied on data. There are challenges. So there have been some programs that aim for just data sets, generating data sets and preserving data sets. And there are concerns about these. There are lots of variety of issues. One of the benefits of the platforms for advanced wireless that was not envisioned when the program was created was the generation of data sets. And one of the things that moving forward we'd like to hear from the community ideas about how would you like to proceed with a more concerted effort, more standardized ways, maybe the science of generating and preserving wireless data sets, and so on. So we're really paying a lot of attention and we're listening, and if you have any thoughts or ideas, we're happy to hear them. Again, thanks so much, and it's time for lunch.
Yeah,
So.
great. Thanks for all your research. Thank you.